Compilers are a magical piece of software. They are software that lets you write more software. We talk a lot about bugs in software. People here talk a lot about bugs in smart contracts. But bugs in compilers are something that people rarely speak about. I have 15 minutes here, and I want to use that time to give you some understanding of how bugs in compilers look like, so you can walk away with some new knowledge. We will have Bhargava who will have a talk after me. We used to work together at the Ethereum Foundation. I used to previously work at the Ethereum Foundation in the Solidity team, and I will be talking about how some of the bugs would look like, and I hope Bhargava will tell you how some of them can be discovered. So let's get right to it. How does a compiler actually work? So there are typically multiple layers in the compilation process. Oftentimes, you start with parsing. Parsing is when you convert whatever text you have into some form of abstract syntax tree. And after the parsing, there are multiple layers of type checking. Every single layer of type checking would often annotate this abstract syntax tree, and it will try to find a couple of bugs if there are some bugs, and then it will try to report it. And after the type checking, there will be a code generation step, and this is where the semantics of the language is actually figured out. And after the code gen, there is often an optimizer step, followed by a final step, which is the assembler, which assembles the code into the bytecode. So how does bugs in compilers look like in each of this stage? For parsing bugs, it may sound simple. You are supposed to parse a certain source file into an abstract syntax tree, and you make a bug in this parsing. Fortunately, this is somewhat low likelihood. We know quite a bit about parsing these days, and mistakes in this is somewhat rare, but it still happens. Bugs in type checking, they can be of different forms. One would be where you have some code that shouldn't compile, but it ends up compiling. And on the other side, you can have something that should compile, but doesn't compile. And this is more frequent in compilers. And the next one is code gen bugs. This is actually quite tricky, and these are where most of the severe bugs in compilers exist, because this is the layer where you actually add semantics of the language into the compiler. And there is a lot of room for mistakes. And whenever there's a bug here, this tends to be quite serious. And the next step is the optimizer, and the optimizer bugs are when the optimizer incorrectly optimizes something, where the semantics of a certain expression is different from the optimized expression that you get out. And traditionally, if you look at compilers as a whole, let's say GCC, LLVM, etc., SolC, the optimizer component tends to be the buggiest component in all compilers. And the final step is the assembler. Again, just like parsing, this tend to have a low likelihood because they are somewhat small and self-contained. So let's look at some of the bugs one by one. So parsing bug. I mentioned that this is somewhat rare, but it still happens. In case of Solidity, the NatSpec parser had a bad reputation for being buggy for a long time. So you could actually abuse the NatSpec a little bit to get poorly parsed outputs. So this is one example where, do I have the clicker? No, it doesn't work. Yeah, this is one example where you could write this NatSpec in a little bit weird way, and you can inject this extra notice into the NatSpec documentation. It's a very minor bug, doesn't really lead to any issues, but it's just fun to showcase. And here's an example of a type checker bug. We had a code like this, and then it would give you something like this. It shows internal compiler errors. I will get into more detail on like what internal compiler errors are. But if you try to look carefully, the fundamental issue here is that you have a struct which has a mapping, and you're trying to put this as a public, as like a external input in a function. And what happens is that you cannot really pass a mapping into an external function, and the compiler is not actually type checking this properly. And you end up getting this internal compiler error. So fortunately, the compiler did not compile this and give you a bytecode. That would have been like much more severe. It just crashed, which is better. And this is what I want to get to right now. What are internal compiler errors? So one interesting insight we can have is if a code passes through type checking, it should almost always compile, which actually means that if the compiler can actually detect an issue after type checking, the compiler has the luxury to crash. I say this is a luxury because a lot of software you cannot do this. For example, in Get or something like that, liveness is really important. So you don't have this luxury of just crashing if it detects an issue. But most compilers can just crash. And this is a very effective technique for finding bugs. Bhargav will probably talk more about how they find bugs. So typically, the way to use this to find bugs is by adding invariants in later stages of the compilation process. And if these invariants fail, you can just crash immediately. And oftentimes, you can just fuzz the compiler by generating large corpuses of random programs. In case of Solidity, you generate a corpus of random Solidity programs and try to compile them, send it over to Solc, and if you can make it crash with one of these ICEs, internal compiler errors, you found a case that is a bit weird. So, as I mentioned earlier, compiler crashes are harmless. And in the previous example, this was a compiler crash, internal compiler error. This was an invariant that was caught in a later stage, and it prevented this code from compiling. And the fix for this was, there was some missing type checker. There was a missing step in the type checker where you have to correctly validate that you have a type that cannot belong in an external function. Yeah, so that's about type checker bug. Now let's go to the serious one. These are CodeGen bugs. So here is an example of a bug reported by Harry from Truffle. So the issue here is that there is an event called function event, which actually has a parameter which is an external function. And then if you try to write this code and try to compile, I think it also crashes with a weird error message. The error message you get here is internal compiler error. I sense a disturbance in the stack. It was like a Star Wars reference, but it was also an IC, which was fortunately caught by an invariant later in the compilation process. So what happened here in the bug was there was some missing implementation for CodeGen in case of external function types. So to fix this, you just had to implement it, and all of a sudden it works. If there was no ICEs, compiler crashes, then this would have been quite severe. You get to compile a program without really realizing that the bytecode you generated was actually incorrect. So CodeGen, as I mentioned, is where the semantics of the language are actually enforced. It's a lot, so there is a lot of room for mistakes. And you have a bug when the bytecode is generated with incorrect semantics. There is a lot of different edge cases in the semantics, and because of that, there is a lot of room for bugs. These are by far the most serious bugs a compiler can have. Pretty much all of the bugs, they're harmless. And one way how Sol-C manages to have very few bugs, for example, we have no known CodeGen bug in the mainnet, which is a very hard achievement. And one way we get to have this is by implementing two different CodeGens. Solidity has a legacy CodeGen, and as you might know, there is this YIR CodeGen. It's a lot of work to implement and maintain two different CodeGens, but it allows you to improve the security by differentially fuzzing both of them. So you can randomly generate Solidity code. You can execute them. You can also execute them against an EVM environment and see if there is a difference in the semantics after the execution. And this is a very effective technique in finding a lot of the CodeGen bugs. And the last one is optimizer bugs. As I mentioned, optimizer bugs broadly, optimizer is broadly the buggiest component in pretty much all compilers. And Sol-C does have a couple of bugs in the optimizer in the history, but fortunately not that many. So here's an example of an optimizer bug. This was called the Keccak caching bug. So there was an optimizer step that would cache certain values of Keccak, and it did not correctly figure out if you could, if the Keccak computation was actually the same. So you have two Keccak computation here, the Keccak 0 from 0 to 32, and then Keccak 0 to 23. Apparently there was this optimizer step that has been around for years, a lot of years. And this step would actually replace the second Keccak computation by the first one. It was a bug found by fuzzing. It was a bug that was dormant for years. And this was, again, something that was found using differential fuzzing. And as I mentioned earlier, optimizers tend to be the buggiest component in pretty much all compilers. And differential fuzzing is very effective in discovering these bugs. Sol-C has between 5 to 10 optimizer bugs across the history of the compiler. In the early days, the legacy optimizer had a little bit of a bad reputation for having bugs, and over the time, the Sol-C team put a lot of work to make sure that the legacy optimizer step is as simple as possible, and investing more time into the UL optimizer, which is much more easy to maintain and to reason the correctness about. So that's pretty much all my talk. I hope you can identify how some of the bugs would look like, and I hope you learned something new.